Hello. Okay, so is everything seem okay? Do you see the desktop and can you hear me? Does everything seem right?
Yes.
Yeah. Okay, great, thanks. Okay, um, so let's see. Today we're going to introduce the idea of modern virtual memory, the paging system. Okay, so we're going to start with the paging. And there's another reading for the next step in the paging system. So that's this beyond physical memory. Uh, we'll talk, so we'll introduce paging today, and then there's two steps to the paging process. What happens with the physical memory? Then there's a part that involves the hard drive. That's this thing here, the part that involves the hard drive. What people mistakenly think is virtual memory. Yeah, there's a huge amount of misunderstanding of what we mean by virtual memory when we talk about computers. And this chapter is about what most people think virtual memory is, but virtual memory is really what we've been talking about, and that's what this chapter is about mostly. Okay, so okay, we're gonna. This is the picture we. Oh, let me think. Okay, the current homework assignment. We'll talk about that later today. After we've introduced a little bit of idea about of paging, we can start talking about the homework assignment. So we'll talk about a little bit about this after we've introduced the idea of paging. Okay, so let's start talking about paging, and then we can talk a little bit about what's in the homework assignment. Let me just unzip it now. Okay, now we're gonna change what's inside the memory management unit to a completely different system. So it's this picture. So because the picture is starting to get kind of cluttered, we're going to change it a little bit. But it's still this idea that the CPU is over here, physical memory is over here. The memory management unit sits in between the CPU and physical memory, and it translates addresses as they go through, from virtual addresses to physical addresses. So the whole point of this is what the book calls address translation. And we're doing that to create this impression of a virtual memory space here. So we have the idea of a virtual memory space, and we create it out of this. Essentially, this is hardware here. The important thing to remember is the CPU only ever speaks in virtual addresses. Okay, it doesn't actually connect to the physical memory because it's got the memory management unit sitting between it doing translations. And that's important. The CPU thinks it's always talking to virtual memory. And uh, what we'll see is important is that the CPU can think that things are contiguous. Like CPU might think that it's stepping through memory from beginning to end, and we'll see that it could actually be jumping around in memory. Like when it goes from this to here, instead of going forward in memory, it could be going backwards in memory because this guy here could be over here and this one here could be over here. So what's in physical memory is very different than what the CPUs think. The CPU might think it increases the address to move from here to here, but in fact it would be decreasing addresses because this thing in between is translating everything. Everything the CPU sends out as a virtual address gets rewritten as a physical address before actually going over here to physical memory. And remember, memory management unit gets updated every time you change processes. So when you change from one process to another process, what's in the memory management unit gets stored in the process control block. So when you're running the blue process, the memory management unit is what's in his is the data that was copied from this process control block into that virtual memory management unit. Then when it's time to switch to the other process, the memory management unit, along with all the CPU registers, get copied to the process control block. You go to the other process control block, and you copy everything from there into the CPU and the memory management unit. On a modern computer, the memory management unit just is part of the CPU, and it just is more registers in the CPU. But logically, it's real useful to think of it as sitting between the CPU and the physical memory, and think of it as this translation step. So it's useful to think of it as a thing in between the CPU and memory, but it's all folded together. Yeah, the memory is still separate. Memory on a modern computer, memory is not, I mean, I wouldn't be surprised if someday it does, but right now, memory is still very much a separate thing from the CPU. I mean, we might, like 100 years from now, there may not even be a distinction of memory. You can imagine that the registers in the CPU are just gigabytes. There's could be just gigabytes of registers in the CPU, and then you wouldn't even have a notion of memory. That would be a dream computer. I mean, that's what if it, we only distinguish between registers and memory because we can't afford to have all the memory inside the CPU. So this architecture is not inherent to the idea of a computer, it's inherent to our budgets. We can't afford to put physical memory inside of the CPU. So we separate them. But very well could be that in 100 years, the CPU will just have all its memory that's just there as the registers. There'll just be, say, billions of registers. And there won't be a distinction between CPU and memory management unit and physical memory. There may not be a distinction between physical memory and virtual memory anymore. So this is engineering. This is an engineering solution to a problem of how to run computer programs. It's not what computer programs are. It's what we currently treat them as because we can't afford to do any better. Okay. Right? So we think of the memory management unit as sitting between here, and we think of the CPU as actually talking to the virtual memory space. So the CPU and the virtual memory space, think of them as a unit, and then this is what's behind. Yeah, this is what's really going on, but this is what the CPU thinks is going on. Okay, now we want to switch from this base and bounds idea, which real simple memory management unit, which is it's still there in the Pentium. The modern CPUs that you buy from Intel, and probably the AMD machines, since they mimic the Pentium architecture, they probably have them also. They do have these these base and bound registers in them, but they're, as far as I know, they're being used. As far as I know, Windows doesn't use them a bit. I know Linux at one time did use them, and I don't know if it still does use them or not. If you wrote your own assembly language code, you could use them, I think. Maybe not on Windows, or maybe Windows doesn't, the Windows CPU may not allow you to access them when you're running. The Windows operating system may not allow you to access that part of the memory management unit. Maybe you can on Linux and maybe you can't on Windows if you wrote your own assembly language code. Okay, so it's not that old of an idea. It's still there in the CPU, and it could be turned on if Windows wanted to. It could make use of this base and bounds. Okay, but it's 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 it, it's not the most modern. It's not the best way. The thing we're going to talk about today works better. Okay, so now let me show you another picture that tries to update this. Okay, okay, here's how we're going to think about this. Just concentrate on one. This is here I drew a picture with what supposedly there'll be two processes, one that was running and one that was ready. Okay, and then over here is physical memory, and in this picture it's more important to bring in the hard drive. So I actually have the hard drive, and it's less important to think of the CPU. So in this picture I've de-emphasized the CPU and made the hard drive more important because the hard drive is going to play a bigger role in what we're doing. Okay, so the memory management unit is just going to be called now the page table. Okay, this thing, the page table, that's what's in the memory management unit. Okay, so this is a process. A process is a virtual memory space and its page table. Okay, and another process would be its virtual memory space and its page table. Then over here is the physical memory, and down here is the hard drive. And we won't really have much to say about the CPU in this picture. The key idea is that we take virtual memory and we cut it up into what are called pages. Okay, we cut it up into equal size pages. Modern pages are, oh, let me open this in the Paint program so I can actually write on it. The crux of this whole thing, the real issue is somebody had the idea that we should cut virtual memory into equal size pages. Okay. On a modern computer, these pages are 4 kilobytes, which is 4,000 and I think 96 bytes. Okay. Okay. So this is 4 kilobytes of memory, 4 kilobytes of memory, 4 kilobytes of memory, 4 kilobytes of memory, and this is from the beginning to the end of the virtual memory space. All the virtual memory space is just cut up into these 4 kilobyte, what we call pages. Okay. Physical memory is cut up into the same size unit. Physical memories in a 4 kilobyte. Now, here they're called page frames. And remember these words, I'm going to be using them a lot, and it's real important. Pages are what you cut virtual memory into, page frames are what you cut physical memory into. And we're going to match them up, but it's real important to always remember if we're talking about a page, which is something that's in virtual memory, and a page frame, which is something that's actually in physical memory. Okay, so the idea was cut virtual memory into equal size pages, cut physical memory into equal size page frames, and 4 kilobytes is the unit. And then the hard drive, it's also cut up into equal size units of the same size. They're called sectors on a hard drive. We call them sectors, but a page frame, and a sector are all the same size. Okay, so a page in virtual memory, a page frame in physical memory, and a sector on the hard drive are all the same size. On almost all modern computers, it's 4,000 bytes. It doesn't have to be. There are a few computers that use different size pages and sectors, but the most common right now is 4,000 bytes. That seems to have worked out as kind of like a optimal. We'll see kind of like what the trade-offs are, but that's been the size that I think all modern systems have settled on. 4,000 byte pages, 4,000 byte page frames, and 4,000 byte sectors. The pages and page frames must be the same size. And it really works a lot better if the sectors are the same size also. So these three things, the pages and page frames must be the same size. Sectors don't have to be the same size as the pages and page frames, but it sure works a lot better if they are. Okay, now virtual addresses go from beginning to end. And what here I see, these are not virtual addresses. Over here, what I've written are what are called page numbers. So this is page 0, page 1, page 2, page 3, page 4, page 5. Each page is 4,000 memory cells, 4,000 bytes. Okay. And then over here, these are page frame numbers, 0, 1, 2, 3, 4, 5. Each page frame is actually 4,000 bytes. So physical memory is still an array of bytes, but now the array of bytes have been cut up into to chunks, into frames. Okay, so we treat them as a block. We treat that every 4,000 bytes as a block, starting at 0. So the page frames are always on these boundaries. Okay, now this is going to mean that a physical memory address cuts up into 2 pieces. There's going to be the piece of the address that chooses the frame number and the piece of the address that chooses the byte in the frame number. Okay, so we'll see. And same with virtual addresses. If you access a byte in memory, you do it by first picking what page you're in and then what byte in that page. So that essentially makes an address into 2 pieces. One piece chooses the page and one piece chooses the byte in the page. Okay, and we're going to give names to those 2 pieces of an address. The part that picks the frame and then the part that picks the byte within the frame. Okay, then what the memory management unit is going to do is it's going to actually translate pages into page frames. Okay, it's going to translate virtual addresses. Remember, over here, virtual addresses get changed to physical addresses. But what it's really going to turn out to be, the real work of the memory management now is going to be changing pages into page frames. The virtual address will break up into 2 pieces, the part that picks the page and the part that picks the byte in the page. The memory management unit was actually going to translate the page part into a page frame over here. And then the part that's picking bytes is just going to pass through unchanged. Okay, so we're still translating virtual addresses to physical addresses, but what we're really going to be doing is translating page numbers into page frame numbers. Okay, so here's how we'll think about it. Okay, suppose this computer, here's a process that's running over here. And what I'm going to do is the process is going to, suppose it's only going to use its first 3 pages. So what I'm going to do is I'm going to write some, suppose it's got code in here, it's stack in here, and it's heap in here. No, normally the code's going to be a lot bigger than 1 page, the stack's going to be a lot bigger than 1 page, and the heap's going to be a lot bigger than 1 page. But suppose this process has code in that page, stack in that page, and heap in that page. Okay. Now suppose here's the thing. Over here, it might be that here's the page frame that's going to hold the code. And here's the page frame that's going to hold the stack. And here's the page frame that's going to hold the heap. Okay. And the interesting thing is this other process that's not running, it might have its code in this page. It might have its stack in this page, and it might have its heap in this page. Okay. And then let me say over here, let me say that this thing is empty, meaning that those addresses are not going to be valid addresses. This virtual memory space it's using that much of itself, and this is going to be empty, this is going to be empty, and this is going to be empty. And over here, suppose that this one is empty, this one's empty, and this one's empty. There's no data in there, there's no code in there. From the point of view of this program, everything is in the addresses from 0 up to here, and there's nothing in those addresses down there. From the point of view of this program, there's some addresses here that are not being used, then there's some code, then there's some addresses that aren't being used, and there's a stack, and then there's some addresses that aren't being used, and then there's a heap. Okay? And let's suppose that in physical memory, we have the code from this guy's code is actually over here in physical memory. This guy's stack is actually over here, and this guy's heap is actually over here. Okay, so this is what's actually in memory. This program's running. This program is ready to run, but it's blocked. But it's still going to have it's still going to be in physical memory. If one program's running, another process is ready, it's got to be in physical memory so the CPU can switch to it. Okay, this process's code, stack, and heap are here, here, and here, and this process's code, stack, and heap are here, here, and here. When the CPU is running this process and it wants to access code, the memory management unit should be directing these addresses over to these addresses. Then when this process wants to access something in the stack, an address in here needs to get translated to an address over here. Okay, this is the virtual addresses, this is the physical addresses. So remember, the CPU here would want to access, the CPU would want to access the code. So it would issue an address that was between 0 and whatever this is. It would issue an address here. That address would go through the memory management unit. That's this page table. The address better come out over here in frame 3. So the way we do that is the page table is an array of page frame numbers. These are page frame numbers. These are indexes into the page table. They are the page numbers. Okay, so this is page number 0, page number 1, page number 2, page number 3, page number 4, page number 5. Page number 0 is actually over here in page frame number 3. So the number 3 is in here. So the number 3 is written in here in binary. That tells the memory management unit when it gets an address from page 0, it translates it into an address in page frame 3. Okay? On your hand, addresses in frame 1 should go to we said 1 over here. Okay. And addresses in page 2 should go to frame 5. Okay. That's it. This is pretty much the whole idea, that the memory management unit, when it sees an address that says go to page 0, says, no, I'm not going to go to page 0, I'm going to go to page frame 3. Okay. When the CPU asks to see something in page 1, the memory management unit steps in and says, no, page 1 goes to frame 1. Okay. When the CPU says this, I want to see something in page 2, the memory management unit says no, page 2 is over here in frame 5. So these addresses, an address that requests one of these, a virtual address that asks for a byte in page 0 will get directed to frame 3. A virtual address that asks for a byte in page 2 will get directed to frame 5. Okay. On the other hand, his page table, which isn't being used right now, but when it will be used, his page table will look a little bit different. His page table will say, okay, if I'm asked for something in page 1, it really is in page 2. So things, if an address in page 1 should be sent to frame 2, and an address in page 3 should be sent to frame 4, and an address in page 5 should be sent to frame 0. Okay. Now, what if the CPU over here, what if there's a bug in the code and the code accidentally tried to access an address here, which is empty? What happens when you say, you go to the page table and say, I need an address for page 3. I need an address for page 3. Well, this is going to be, what we're going to do is, this is going to be empty here. Oops. This will be, well, actually, memory can't be empty. So empty is really not a very good word. So instead of saying empty here, I'm going to say not valid. Well, no, I'll go ahead. I'll keep it safe. I'll say empty. Okay, so that's an empty entry in the page table. This is another empty entry in the page table. This is another empty entry in the page table. But nothing can ever be empty. Okay, so if the CPU looks inside there, they'll see some random stuff. And how do they know that random stuff is meaningless? That's going to be something over here in the page table. There's a column of bits here. This is called the valid bit. Okay, and here's how that's going to work. This is going to be a bit 1. This is going to be a bit 1. This is going to be a bit 1, and this is going to be the bit 0, 0, 0. This denotes that this is really empty. It's really saying that these bits don't matter. You just ignore those bits. I'm not even sure if I should write empty there or just whatever. What this bit here says, if the program asks for an address in page 3, the hardware goes over here, sees something written there, but then sees a 0 here and says, that's not a valid entry. So then it does what we did over here, would be the memory error. See, then the memory management would send a memory error back to the CPU. That was like exceeding the bounds over here. Okay, remember, you got this memory error here, if in this case, if you had an address that exceeded the bound. The base address would tell you where the base is. The bound address would tell you how far off of the base you could be. If a virtual address came in here that exceeded the bound, you got an error. Now, there's no bounds. Now, if somebody asks to access an empty virtual page, in the page table, those empty virtual pages are denoted with a bit of 0 here under the V bit, which is called the valid bit. Okay, so then there would be an interrupt from here back over to here. The memory management unit would send an interrupt from here back to the CPU saying not valid. saying memory access violation. Okay, now over here, this one's an invalid. This one's a valid entry. This one's an invalid entry. This one's a valid entry. This one's an invalid entry. And this one's a valid entry. Now, if this is an invalid entry, it really doesn't matter what I put over here. I could say it's empty. I could say it's not valid. I could say it's holding random garbage. So you can think of if this is an invalid entry in the page table, you can think of that data as just being unimportant, meaningless. It's the page table is literally something that's stored in memory. You can't have an empty page table. So it doesn't really make sense to say this is empty because there's always something in memory. It does make sense to say that these are empty because what it's saying is that they don't even exist, that this is virtual memory over here. So actually, you know, this makes sense. The word empty over there makes sense. The word empty here doesn't really make sense. Anybody have a suggestion? It's not empty. Virtual memory can be literally empty because it's just virtual memory, so it doesn't exist. Maybe just say garbage entry. This would be a garbage entry. It's just random, it's just, random bits that don't matter. I don't know if that's a good word or not to use there, but this would just be random bits that don't matter because that page isn't in use. And this is the important bit. This bit says 0, which means that this data is not valid. So I could also write not valid, which is why this is called the valid bit. So that means if this is 0, the information over here is not valid information. If the bit here is 1, then that's saying translate the frame number 2, the page number 2 to the frame number 5. Translate page 2 to frame 5. Translate page 1 to frame 1. Translate page 0 to frame 0. On the other hand, over here, frame 0, page 0 is not valid. Page 1 gets sent over here to frame 2. Okay. All right, so this is how virtual memory works. Now, what's nice about this is over here, when a process went away, we ended up with fragmented memory. Okay, when a process went away, we would get fragmented memory. We'd end up with these holes in memory. And if a new process came along, we would have to like slide things around to make room for a new process because you would have a chunk of empty memory here and a chunk of empty memory here and a chunk of empty memory here that you couldn't, maybe they weren't big enough by themselves, but if you slid everything up, you can make room. But that's really wasteful CPU time. Now, over here, what happens is there's something really interesting going on here. Suppose process 1 terminates. Okay, if process 1 terminates, that frame, and that frame become free. Okay, now you might think, oh, there's holes in memory. But then if another process comes along and he needs 3 frames, you don't have to slide anybody around. Since all the frames have equal size, when a process wants 3 frames, you can give them any 3 frames over here. Even if you have free frames, if you have holes in memory, all the holes are equal size. And this is actually the crux, this is the key idea. All the holes have the same size. So you just give a process one of the holes, one of the free frames, and it doesn't have to slide anything around. And then this table tells you where a page, what frame it would be in. Okay. So if I really should have had like 3 processes in this picture, but the picture is not big enough. But the idea would be that if one process dies and goes away, it leaves a hole in memory. Like if the process 2 goes away, then I would have a free frame here, a free frame here, and a free frame here. But then when another process comes along and needs 3 frames, it just doesn't matter. I don't have to shuffle anything around in memory. I can just give them that frame, and that frame. Okay. I don't have to do like what I did here of having to I have a little bit of free space here, a little bit of free space here, a little bit of free space here, but none of them are big enough to be used. Now, if I have a free space here, a free space here, and a free space here, they're the right size. They are frames. Okay. So as long as I have enough free space, if a program needs 4 frames and there's only 3 free frames, then you don't have enough memory to run the program. And that's one of the issues we're going to tackle eventually. What happens if a program wants 4 frames, but there's only 3 frames available? Okay, the hard drive will step in, and we'll see that we can actually store some of these frames on the hard drive. Okay, and that's actually where things get real interesting, is that if a program has more frames than needs more frames than there are physical memory, some of the frames can be stored on the hard drive. That slows things down, but we'll see that it allows programs to be huge. They can be much bigger than physical memory because they can have frames over here in the hard drive. That's the next chapter. But that's the next chapter of putting frames over in the hard drive. Okay. Now, let me show you a document that oh, let's see. Now, in the book, here's his, here is essentially this picture here in a form. Okay. This is the virtual address space. Those are the pages. Okay. This down here is the physical address page space. What I put over here, those are the frames. See, he had a little bit more room here. Some frames are reserved for the. Notice I didn't put the operating system in memory. I should have. Yeah, if I had this, if I could, if I didn't want to clutter the picture so much, but some frames should be reserved for the operating system. Some frames may not be in use. Then see here, he's got page 3 of one application. So this is a process, and page 3, so the page 3, like here I wrote it as heap, code, and stack. Here he wrote, this is kind of what's in the page table. This would be page 3 of one program, page 0 of that same program, page 2 of that program, and page 1 of that program. So AS, I forget what AS means to him, but that's his application, I think. OS is the operating system. AS, what does AS even think? Oh, address space. That's the address space of the process. Yes. So he's thinking, for him, OS is operating system. AS is the address space, the virtual address space. Okay. So the virtual address space has a page 0, page 1, page 2, page 3, page 4, page 5. Over here, that's the virtual address space. Page 0, page 1, page 2, page 3. Then down here, he's saying that virtual address space has been placed in physical memory. Page 0 was here, page 1 was here, page 2 was here, page 3 was here. Okay, page 3 is in frame 2. Page 0 is in frame 3. Now, the next thing is to show what the page table looks like for this. Okay, so this virtual address, which in my picture is this thing over here, is placed in physical memory. That's this picture over here. And he's showing you how it's being placed. And now the thing is, he doesn't give you the page table. See, I mean, he kind of goofed. I mean, the next step would have been say, well, this layout gives you a specific page table. Okay. So you can write down over here if you want. You can if you print this out over here, you can write down what the page table looks like for this process. Okay. The page table, the index into the page table are the page numbers. So page number 0, page number 1, page number 2, page number 0, page number 1, page number 2. The entry in the page table is the page frame, except the entry in the page table may not be meaningful. So you need this bit over here to say, well, that entry in the page table isn't being used. If the program accidentally errored and tried to access that page, that would be sent to the memory management unit. The memory management would see that they're actually asking for an invalid entry, and it would crash the program. Okay. So he has the virtual address space and the physical address space laid out pretty good. It's a pretty good picture, but then he doesn't do the next step, show you what the page table looks like. Okay. All right. Now, the next thing to talk about is this is the address translation part. We want to explain that what are we doing with addresses? Like, how does the memory management unit deal with an address in physical virtual memory address? How are we actually doing what would be this step here of virtual addresses in, physical addresses out? Okay. In his book, this page here, this picture here is essentially explaining virtual address in, physical address out of a page table. So the memory management now is a page table. Virtual addresses go in, physical addresses go out, and this is his drawing. This page here is the drawing of trying to explain that. I don't think he ever shows a page table in here. Here is one page table. This is one row of a page table. That's usually referred to as a PTE, page table entry. That's one row of the page table. So here he's drawing a picture of what one row of a page table looks like. The page table is an array of these rows. See, there's all these bits over here. I drew it as just like 3 extra bits here. So there's something called the page frame number. Page frame number. See, there's the page frame number, page frame number. There is, I called it the V bit for valid. Huh. I thought he had a V bit for valid in here. It's almost always referred to as the valid bit. I don't know which one of these he thinks is the valid. It's almost always, I thought he even referred to it as the valid bit. See, right there, valid bit. But then he doesn't have it in the page table entry. There's no V in the page table entry. We'll see what all these bits mean. We'll talk about all these different bits in the page table entry. There's a bunch of bits that could be in the page table entry. There's a few that are always there, and then there's some that may or may not be there depending on the CPU architecture. The valid bit always needs to be there, but I don't even know which one of these is to him the valid bit. Now this says this is supposedly the page table entry in a Pentium. So maybe the Pentium, maybe Intel doesn't call it a valid bit. Maybe Intel gave it a different name, but I don't know which one of those is the valid bit. But he calls that an x86 page table entry. So that means that's the page table entry in an Intel computer. Okay. Intel sometimes gives things funny names. So if the whole world calls something the valid bit, Intel might have given it some other name. Microsoft does the same thing. They give things funny names. Part of that's just plain old marketing, branding. But they like D word. You saw how like when you write Windows code, they gave names to all the data types. Why in the world would anybody do that? They gave different names to all the data types. And Intel does the same thing. They sometimes come up with weird names for things that are different than everybody else. So one of these bits is the valid bit. I don't know if he says in here which one is the valid bit in a x86. Okay. The valid bit is the thing that distinguishes whether this is a useful piece of information or garbage. Is the information in this column garbage? Remember, there's always data in a memory location. You can't empty out a memory location. And if you put zeros in there, that just looks like page frame 0. You can't put 0 in there because that doesn't mean, 0 is a valid page frame. So there's nothing you can write in here that would signal that this is not valid. You need a separate bit, a bit that says this is not valid information over here. So you have to have this bit in the page table. Okay, now here's here's another way to explain what he's trying to explain in the book in this page here. Okay, so here's another way of thinking about that. Okay, a virtual address is a bunch of bits. And what we're going to do is we're going to take the bits of a virtual address and cut it up into 2 parts, the page number and what's called the offset. Okay, so like what's real good to work with is 32-bit addresses. There's a 32-bit address. So there's 32 spaces for zeros and ones. So there's spaces for zeros and ones. Okay, so that's a 32-bit address. Okay, what we're going to do is we're going to chop it up into two pieces. Now, in Windows, I just carved off 12 bits there. Okay, so what I'm doing here is I'm saying over here is 12 bits, and then over here is going to be 30 bits. Okay, 12 bits gives you 2 to the 12 addresses. And 2 to the 12, if you remember, 2 to the 12 is exactly 4096. That's the size of our pages. Okay, so 12 bits is how many bits you need to address all the bytes in one page. So this is called the page offset. Okay, this selects a byte in a page. That means these not 30 bits, 20 bits. That means these 20 bits over here, these 20 bits choose. Now this is, so over in this picture here, the way we're going to think about it is these 20 bits choose a page. These 12 bits choose a byte within the page. So we have 2 to the 20 pages, and each page has 2 to the 12 bytes. Okay. So see if I can fit this in here. 20 bits here. 20 bits here gives 2 to the 20 pages. Doesn't really fit, does it? Oh, let's see. Okay. Okay, there. 20 bits gives you 2 to the 12, 2 to the 20 pages. And 12 bits gives you 2 to the 12 bytes. Okay. 2 to the 20 pages, and each page has 2 to the 12 bytes. So an address, this is a virtual address. A virtual address is cut up into two pieces. In his picture over here, I can bounce around between all these different pictures. In this picture here, see, a virtual address is cut up into two pieces. See, this part's called the offset. This part over here is what here I drew as this. This is the offset. Okay. So this is the offset. Okay, in his picture, that's the offset. Then this part over here is the virtual page number. Okay, a virtual address is cut up into two pieces. A virtual page number, actually, it's usually just referred to as page number. There's virtual page numbers and physical page numbers. Virtual page numbers are often just called page numbers. Actually, I'll keep it virtual page number. If I say page number is synonymous with virtual page number. And in the book, he also sometimes flips that way. If he just says page number, he means these numbers over here, page numbers, which we'll also call virtual page numbers. But then over here in physical memory, we have the page frame numbers. We don't call these page numbers. If somebody just says page number, they almost never mean these guys over here. So if somebody just says page number 5, they would almost never mean this over here. They would mean the 5th page over here in virtual memory, which you can either call a virtual page number or a page number. But if you mean a physical page, it's always going to be referred to as a physical page number. Okay, so physical page numbers, virtual page numbers, or just page numbers. Okay, and in his book, usually he has virtual page numbers and physical. Well, see, then he calls these frame numbers. He calls them PFNs for physical frame numbers instead of calling a physical page. See, then there's two names for those: physical frame numbers or physical page numbers. Okay. If you go read about this stuff, there's no police making everybody use the same words for this stuff. So words like physical frame number could also be called a physical page number. A virtual page number could just be called a page number. Okay. So there's two words over here. This is either a virtual page or just a page. Yeah. So this could be either called a virtual page or a page. This is called either a physical page or a page frame. Okay. Nobody ever calls these pages. If you use the word page, you mean a virtual one. But virtual pages can either be called pages or virtual pages. Physical ones are either called page frames or physical pages. Okay. They're never called just pages. Pretty much everybody, if they just say the word page, they mean one in virtual space. One of these units in the virtual address space. If they use the word page, it's almost always going to mean over here in virtual space. And then if they mean something in the physical side, they'll either call it a page, they'll either say a frame, a page frame, or a physical page. So they could just use the word a frame or a page frame or a physical page. And unfortunately, you have to do these translations. Even the author will sometimes bounce between these words. The people who work with this are so used to these different words that if he doesn't proofread real carefully, he may not realize that in one paragraph he referred to it as a frame, in another paragraph he referred to it as a page frame, another paragraph he referred to it as a physical page. Yeah, he may not notice that he's slipping between these different words. So be careful that there's the virtual memory cut up into pages, physical memory cut up into frames or page frames or physical pages. Okay. An address, a virtual address, is cut up into the page, the virtual page number and the offset. The virtual page number is which one of these pages you're in. Okay, that's the virtual page number is which one of these you're in. The virtual page number is used as an index into the page table. So this virtual address becomes this virtual page number becomes that index in the page table. This virtual, now notice that would mean over here, there's 0. All those bits mean you're in that that page. See? This then would be a byte in that page. Then if I put a 1 there, I've moved to that page. So this chooses the page. Okay. Then, for example, there's page 2. That address is in page 2. Notice I'm keeping the offset. I'm not changing the offset. So I'm bouncing from a byte in here to a byte in here to a byte in here, but I'm stepping through pages. Okay. This would be page 3. See, now I'm in page 3. 0, 1, 2, 3. And that one's, in this case, that's an empty one. Okay. In this picture here, that would be an invalid virtual address. Okay. This part of the virtual address is used as the index into the page table. Then the page table entry is used to replace the virtual address. So the page number. This thing is used as an index into the page table. Then what you find in the page table replaces this thing. And that's shown down here. This is this part here. It's used as an entry into the page table. Then this replaces it. The right-hand side of the page, the entry in the page table replaces this page number with the page frame number. Okay? The offset is just copied down to here. In his book, that's shown as like a diagram here. This is used as now he just draws his address translation. What that means is this 01 is used as the index into the page table. You go into the entry in the page table, get that number, and then that number goes down into here. So this would be entry 1 in the page table has 110. In our picture over here, he would be showing, if this picture was over here, this is entry 1 in the page table. 01 would be entry 1 in the page table. And he's got 7 in there. See, that's the binary number for 7. So he actually has a 7 right in there. That's what that's saying. So you translate 01 into 111. Yeah, these numbers are actually all binary numbers. So the binary 1, in our case, binary 1 is being turned into binary 1. Binary 2 is being turned into binary 5. So binary 2 is 10. In this case, this would be 10. That'd be 10 is going to be turned into 101. That'd be 101 down here. So if in his picture he lined it up with ours, this would be a 10 here. That would be this entry in the stack. 10 would go to, in this case, 101. Okay. In our case, 01. In our case, 01 goes to 01. So if this picture was over here, 01 would go to 001 because we're translating 01 into 001 here. Okay, that's the idea. It takes some getting used to. Like everything else in computer science, it's a simple idea, but at the same time, it's not all that simple. There's a lot of moving parts. Okay, and the moving parts are virtual address space, physical address space, pages, page frames, page tables, page table entries, which are made up of page frame numbers and a valid bit. So there's lots of words here. and excuse me. And what you need to do is actually should write down these words and start trying to remember them. If you work with computers in the lower levels, like if you were in charge of servers if you ever got in charge of servers, you'd be worried about this stuff. You need to know how much memory your computers have. You have to know how memory is allocated. If you're writing web applications, you don't ever need to know about this stuff. But on the hand, if you're working with databases, this stuff it's useful to know this stuff because it gives you a sense of what you need to buy, for example. How much memory do you need? How is memory set up? How does memory get used? When you have a basic understanding of how virtual memory works, it makes it better. You're better off at understanding what people are talking about, even when they just talk about hardware. Okay. So you can see how there's page number, offset, page frame number. We have all these different kind of terms going on here. Okay. Okay. Now, again, the virtual addresses split into two parts. The number of bits here is determined by how big your pages are. If your page is 4,000 bytes, then this is 12 bits. If your page is 8,000 bytes, then this is 13 bits. If your page is 2,000 bytes, then this is 11 bits. Okay, so the size of the offset is determined by your choice of page sizes. Okay, then the rest of the address is the page number. Okay, the page number is used as the index into the page table. And then you look up the thing that this thing is going to be replaced by. You replace the page number with the entry in the page table, which is the page frame number. And that gives you a physical address. Okay. And over here, here's a page table entry. This is the index to the page table entry. This is what was in the page table entry. Okay, so that ties them together. This is the index of the page table entry. This is one row of the page table. A page table entry is one row. This is its row number. This is what was in the page table. Okay, yeah. So you use this to look up a row in the page table. Then you take this number and you put it there. So this number gets replaced by this number. This number just gets copied down to here. And he showed that in his picture of showing the offset just going straight down to here. See, the offset just goes straight. The virtual address, you just copy these into here. Okay, you replace the page number with the page frame number. So the address translation is really being done on the address translation is being done on this part of the address. Okay, so it's this part of the address is being translated from page number to page frame number. Okay. Okay. Now, from the point of view of a programmer, let's look at the homework assignment. How this, what a programmer needs to know about this. From the point of view of a programmer, your program is carved up into pages. Your program is carved up into pages. That's the unit of memory that you can request from the operating system. Suppose your program needs to grow. Suppose your program needs a larger stack. Okay, so how can your program, if your program needs a larger stack, you have to ask for another page. Okay, now here's, you can't ask the operating system for half a page. If you want to grow your program, you have to ask the program for another page. Now, notice that here, this stack can't grow because this stack is right next to the heap. But if you think about this one, see how that stack has got an empty spot just below it? This stack could grow down here by saying, oh, I want the operating system to make this thing valid, and I want the operating system to allocate a frame to this empty spot here. So when a program is running, the program can say, hey, I've got an empty spot in my virtual memory space. Why don't I ask the operating system to fill it in? Why don't I ask the operating system to give me a page frame by writing into my page table the address for number 4, was suppose that there was an empty page frame over here. Maybe frame 6. Yeah, suppose frame 6 is free. So then this program could make a request. It could say, allocate something here. So make this into, say, I want some data in here. I want to load some data. So over here, maybe the operating system gives you page 6 and then makes this one now it'd be marked as valid. Okay, that's what you're going to write code to do. You're going to, homework assignment 4 is to do the Windows call that just did that. The Windows function call that says, I've got a free chunk, I got an empty frame here. Operating system, give me, I got an empty page here. Operating system, please give me a page frame to back, what we say to back that page. So the operating system will update your page table for you, and now this will be valid memory. Maybe in this case, I've made it down here in frame 6. Okay, so frame 6 now is the data for that process. Okay, right. In Windows, you do that with a function call with this virtual alloc function. Okay, this is the function that literally just does what we just mentioned here. That's the function that says, to the operating system, here's a certain place in memory that I want to become now. It's empty. It's currently empty, but I want you to turn it into from empty to being a valid memory location. So that virtual address translates to something in physical memory. I want to turn it from empty to being something that's backed, we say backed by physical memory. Okay. And the virtual alloc function, you're going to say, here's the address in virtual memory where I want the thing to be. So you give it usually you would make it the address of the first byte in the page. So you give it the address of the beginning of the page. Okay. If you give it an address in the middle of the page, it rounds it down. If I remember right, if you give it an address in the middle of a page, it just rounds it down to the beginning of a page. Then you can say how much you want. Like suppose you want 3 pages. So you could actually ask for a bunch of pages in a row. So you could say, I want several, I want 5 pages. Yeah. Starting at this address, you can say how many pages you want. Then here we'll talk about later. You can actually say the pages come in different flavors. Okay, they can be writable, they can be readable, they can be read-writable, they can be executable. So we'll see that as we talk more, these pages can be given properties. So for example, you could set a page to be read only so that you can't write to it, or you could set a page to be execute only, so it's where code goes. So here you would set the properties of the page, and this is more properties. So these are two kinds of properties that you could set. So these are the key: where and how much. Where in memory you want physical memory to be allocated. Where in virtual address space you want something to go from being empty to being valid, and how much. Okay. Now, every program that's running on your computer is running in virtual memory space. Okay. You can actually look at the virtual memory space of your program. You can look at this picture of a program. You can't look at this picture of physical memory. This picture is owned by the kernel, so you can't see what's over here. But for every process running on the computer, you can see this picture here. There's a program that you can download that lets you do that. Now, I forgot to put it up. I downloaded it already. It's by the same people who wrote Process Explorer. Okay, let me just download it now. I'll put it up. I'll put a link to it up on the website. I haven't had a chance to put it up there yet. It's called it's this program called VM Map. Okay, so you just download it. Oh, wait a minute. It's in the homework. I'm sorry. It is. It's part of the homework 4. Yeah, it's right there. See, I made it part of homework 4. Okay, so if you double click on this, it pops up a window saying, what process do you want me to show you the virtual memory space of? So it lists all the processes, just like Task Manager. So for example, I can say, oh, I want to look at the virtual memory of TextPad. Okay. This is the virtual address space of TextPad. Each one of these entries is, well, it's actually what they did is each one of these rows is not one of these pages. What they've done is they've lumped the pages in groups. If you open up one of these little boxes, that's a page and that's a page. That's 2 pages. Okay. And if you open up another box, now they're lumped together because remember I said they have properties. What they do is they lump together consecutive pages with the same properties. Okay. So essentially, when you open these little boxes up, you're looking at the individual pages of virtual memory. You're not looking at the page table. You don't see the page table. You're actually looking at this array of virtual memory. You're looking at this array of virtual memory pretty much starting at address 0. It doesn't quite start at address 0 because the very first chunk of virtual memory is reserved. You're not allowed to use it. You actually don't have access to the very first section of virtual memory. and it goes all the way up. Now this is a 64-bit address space. It goes up to some huge memory location. Okay, so this is a map of virtual memory. Now this is up here is some information about it. For example, notice that heap. I can ask where my heap is. I can ask where my stack is. Okay, so this is kind of like a summary of what's down here. Okay. Now this I picked on. Now let's see. I don't know how to get back to the. Now I don't know how to get back to the unselected version of what's down there. Like right now, I'm looking at what I selected here. I want to go back to the whole address space. I forgot now how you get this window down here to be the whole address space. See, now it's the image. That's my code. Now it's showing me my heap. Now it's showing, oh, I can actually, no, it doesn't show anything. If I ask for my page table, it doesn't show anything. Oh, how do I go back to? See, now it's just the specialized version down here. Probably one of these will let me go back up. Oh, let me try refresh. No. One of these entries should have just been virtual memory space. So you went back to your whole virtual memory space. So if I just if I close it and reopen it, now I'm back to okay. See, now that's my whole address space. See, now this is my whole address space. So I'm looking at a view of essentially what this picture here is for one process. And I could do this for any other process. I can go back over here and I could ask for a memory map of one of these chunks of Chrome. Okay, so I can look at what's in virtual memory of Chrome. Okay, these now programs are amazingly complicated. Their virtual memory spaces are really complex. Okay, now your homework assignment, you're supposed to write a program that makes these requests. Now, what to organize it, what I've made it is you're going to write a program that accepts commands at the command line. You give this program commands, and the commands are to do things like reserve, commit, touch, lock, unlock, commit pages. Okay, so you have to read the details of this, and the idea is that you would actually let me run the demo version of it. Okay, so here's a demo version of it. Okay, now the demo version comes in two pieces. This piece is where I type commands to manipulate memory. And over here is a baby version of this program here. It's a baby version of this program here showing you what virtual memory space looks like. So right now, this is what the virtual memory space of this program looks like. So this program has this virtual memory space. If you restart VMmap and you map the demo program, this picture here is what's over here. This is a little bit easier to read, but this picture, this stuff down here, if you actually go through, you can kind of see that they're going to show you the same information. Like, see, there's a 65,000 byte free region. Let's see. You have to figure out where to start. At some point, you can line these things up. See this one at 6? That's this one here. See this one? The 60000 is that one there. That's the thread stack. That's something called the thread stack. That's this one here. Then here there's something at A. That one's the next one over. So you go 6A. The stuff that's a little bit before here is a little bit different. Like this stuff here is this stuff here in blue. So this stuff here in blue is the stuff from here up to here. Then this little chunk here is this orange one. Then this one here is the next blue one. This yellow one is this one. This is the yellow one. So then they go, this is the yellow one. Right after the yellow one is a light blue one. That's this one. Is it? Okay. With a little bit of effort, you can line these up. They're showing you the same thing, but they're displaying them a little bit differently. Okay. Now, what we want to do is give this program commands. And the commands will show up over here as memory being allocated. Okay. So over here, if you look in the documentation, a command looks like this. First, you type a number 5. So for example, I take a number. Like if I type 10, that means execute this command after waiting 10 seconds. Okay. So first is time. Then there is what command to do. So I'm going to use command 1. Command 1 is to reserve some memory. Okay. Then I say where to reserve it. I'm going to reserve the memory in the middle of this is a big chunk of free memory in the middle of my address space. It's that memory the middle of my address space is the address, let's see, 8, let's see, make it 4. I'm trying to figure out how many zero, I remember how many zeros are out. Here's a sample command. This is the command I actually want to execute. Okay, I'm just going to copy and paste this. Here's my sample command. Wait 5 seconds, then reserve in the middle of the virtual address space some memory, and 2 is the units. I want 2 units of memory, and 1 is the access code. It's going to be read only. Okay. Now, now let me execute that command, and you'll see it. Wait 5 seconds. There, see, I just did that. I allocated that memory in my virtual memory space. Okay, I split this huge empty spot into 2 huge empty spots with a little region of memory in between them. So I carved out a little chunk of valid memory. I just carved out a little chunk of valid memory in a big sea of empty memory. So essentially, there's a bunch of empty stuff here and a bunch of empty stuff here. That's denoted as free here. Free, people refer to memory as free, meaning that's actually, I mean, maybe I should have said, put the word empty there, but people tend to refer to it as free. The memory's not in use. So free here means empty. And I just took a big empty region and I put a little bit of reserve memory in the middle of it, okay, with that command, okay? So you have, now that command was actually in the code. That's this case 1. You're going to put a function call in here that's a function called a virtual alloc that just did that. That thing that we just did, the memory showing up here was a single function call to virtual alloc. Okay, it was a single function call to virtual alloc. So you have to write the one line of code that does that. Now you have to, it needs to gather up from the command line. Actually, I did that for you here. Here's where I gather up the information from the command line. So this variable has the time, this has the operation, this is where you're supposed to do it, this is how many units, and this is the access code. So the variables you need to write that function call are pretty much right there. Okay, and then you'll write a function call here that allocates that memory. And the functions are documented on Microsoft's website, and they're also documented in a file in that folder. Where's the homework 4 folder? Did I close it? Oh, in this, there's a 8-page document here from an old Windows programming book. It's one of the few books I could find that describes these functions. So there's a little bit of, you can read about it in the Windows documentation, and then this guy's got a little bit of documentation here, and he shows you some example code using it. So he's got some example code of, keep reading. See, he's got a little program here of example code of using these functions. Okay, so it's more reading than it is writing. Now on Tuesday, on Monday we'll start up with this assignment. We'll go into it in more detail, but the idea is, you're going to write code that just does essentially what we're describing in this manipulation here, of saying, asking the operating system to, when your program starts up, some of virtual memory is allocated for you, most of virtual memory is empty. But as your program is running, it could ask for more physical memory allocated into its virtual memory. And that's your homework assignment, is to write the code that asks for more physical memory allocated to your virtual memory. And then you can give up, once you've had something allocated to you, like in this case here, I could free that memory up. That's why it's actually called free, because you think of it in Windows, in C programming, you malloc and you free. So this was a mallocing operation, and then I could free that memory back up, and it'll go back to being free. Okay, so there's virtual alloc, and then there's virtual free. So it's denoted as free memory because it's the memory that's been given up. It's not in use right now. So the big red one means that's a huge chunk. I wrote this program to note the huge chunks of free memory in red. And that's what you want to look for. You want to look for big chunks of free memory to play around with. So that's in red. Okay, so let's quit there. Okay, read about the homework. It's another assignment where there's way more to read than there is to write. So it has that in common with the last program assignment. But this assignment isn't as hard as the last one. What you write is going to be pretty straightforward. You're going to write about 10 lines of code, a couple lines of code for each one of these commands. Each command is only going to be, there's eight commands, and each command is just a couple lines of code. Okay, so it's not a lot to write, but it is a lot to read. So reading it is about understanding how virtual memory works, and then you can program virtual memory here. Okay, so if you have questions about, after start reading the textbook and also the description in the homework assignment, and then if you have questions about the assignment, you can send me an email or come to office hours. So let me quit there. And so we'll continue with the homework assignment, and then more about virtual memory on Monday. So have a nice weekend. Bye.